like to talk on the topic kinetic of unwinding of double helix. The kinetic of the unwinding of the DNA double helix was first studied by Kuhn in 1957. Unwinding occurs after the interchange bonds are disturbed. If we assume that it takes place as a result of rotational Brownian motion, then the time required for this process to take place will be much longer than that observed. For instance, for DNA with a molecular weight of 3 × 10⁶, the unwinding of 450 turns of the helix, which is necessary for complete separation, will require 150 days. Meanwhile, the time for DNA with a molecular weight of the order of 10⁸ is about 1 minute. Kuhn examined the separation of chain that occurs when rotational thermal motion is combined with translational motion and obtained the time of the order of 1 minute for DNA with a molecular weight. As you can see the structure of DNA over here. So let's talk about another theory proposed by Fong in 1964. The enlargement of free chain must not occur if the interchange bonds are broken at the midpoint of the double helix. The two halves of the helix fluctuate independently, half the time spent on unwinding and the other half on rewinding. However, at the initial state of strand separation, because of the tight packing of the helix, the second winding cannot occur as the kinetic energy of entangled chain is converted to a potential energy which contributes to unwinding. If many turns have occurred, the chain may be twisted back again. Thus, two halves of the helix are randomly twisted and untwisted with the helix radius remaining twisted and untwisted with the helix radius remaining unchanged. But twisting cannot continue for an indefinitely long time period, and therefore with such random motion the helix is predominantly unwound. So here you can see two graph over here, kinetic curve for DNA with defects, and the another one is denaturation of DNA. So the another topic is interaction of double helix with small molecules and ions. The theory of adsorption of small molecules on DNA has been developed by Krutis and Gruskay. Suppose that a biologically active ligand is bound by a certain numbers of base pairs of DNA. Let us consider the equilibrium binding of ligand by a polymer, which is a random sequence of A, T, and GC pairs. The ligand by a polymer, which is a random sequence of AT and GC pairs. The ligand may contain functional group, part of which undergoes specific interaction with base pair. Here you can see the figure over here. Small molecules of the type of acridine dye either slip in between base pairs in the DNA double helix or line up in a narrow groove on the surface of the double helix. Evidently, both complexes are encountered cannot yet be given to either of the two models.